Algebra 2, we're going to continue into probability with our second little mini unit in Chapter 11. Example 1 deals with finding probability involving choosing objects that are not distinct. So we've got an aquarium. In an aquarium, there are 6 large fish and 8 small fish. Half of the large fish are blue. So you could even, if you wanted to, begin to make a little picture here. You certainly don't have to. You've got large fish. You've got 6 of them. 1, 2, 3, 4, 5, 6. You've got small fish. So that's 1, 2, 3, 4, 5, 6, 7, 8. Now we're separating them. Of course, they're probably intermingled. But it says half of these large fish are blue. So I'm going to just put BL for all these. So they're blue large fish. In fact, even if you have a highlighter, you can, mark that. So half of the 6 would actually be a 3. So they want to know, find the probability that a fish is selected at random and it is a large blue fish. Well, remember, probability would be the number of ways you can have a success, whatever you want to have happen, over the number possible, or the number of possibilities. So how many large blue fish do we have? Well, there would be 3. You can see I drew that picture right there. How many total do we have? Well, you've got 6 and 8. That adds up to 14. And you will have 3 out of 14. They want you to answer as a fraction in simplest form. Sometimes you're actually going to have to go to a decimal. They will tell you that in the problem. Now, cards. Some students are very familiar with a deck of cards. Some maybe hardly at all. The wonderful thing is Alex is going to give you a very thorough picture, in fact, which I'm very happy about. There are 52 cards in a deck. You're going to have red cards. There are actually 2 types of red cards. You could have hearts, you could have diamonds. And there are 13 hearts going from an ace, which is like a 1. Ace could be high or low. Here they're making it low, like a 1. You've got the 2 of hearts, the 3 of hearts. You've got these face cards right here because you have a person's face on them. You've got the Jack, Queen, King. 13 such cards, 13 diamonds, 13 spades, and 13 clubs. So there are 52 cards possible. And we're going to draw 1 card at random. What's the probability that the card is a queen? Well, we've got 52 cards. But looking at the queens, you can see we've got 1, 2, 3, 4. So we'd have 4 out of 52. Now, of course, what you can do is always get some help reducing this. And, if you had 4 over 52, you could see quickly the answer you should really write down, simplified, is 1 over 13. Let's take a look at B. What's the probability that the card drawn is a club? Well, again, we've got 52 possible. But how many clubs are there? Well, you could even count these up if you needed to. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here's 11, 12, 13. There are 13 cards with a club on them. So, tell you what, we could even go second enter so we don't have to completely make the fraction show up again. This time you'd get 1/4. A 1 out of 4 chance that somebody would draw a club. Watch out for letter C. It says, what is the probability that you get a queen and a club? You only have 1 card. It must be a queen and at the same time, it must be a club. I hope you would agree that there's only one card that would do that. It's the Queen of Clubs. You have to be a queen, but you must also be a club. Alex is also going to give you some problems where they'll say, what's the probability that you have a queen or a club? Well, I hope you'd agree that right here for the clubs, the word or means you could have one or the other. The clubs, you can say there are 13 of them, one of which is actually the Queen of Clubs. But it's okay in this problem because it's or to get any other queen. So there will be 3 other cards that would satisfy this. So we have 13 straight clubs, one of which happens to be the queen. But then we get 3 extra, so that's going to be 16 total. 13 clubs, one of which is the queen, but then 3 different queens that are not a club. So once again, what can we do? Well, we can just do a second enter, bring this back, go 16 over 52. You would get 4 over 13. Okay, so you'll always get that picture of the deck, thank goodness. Okay, so let's take a look at what's happening. You're rolling a dice. You're rolling a die, I should say, 6 sides. And they roll this 40 times. And you get these results. You can see pretty quickly a 1 shows up 8 times, a 2 shows up 6, 3 shows up 5, a 4 shows up 10 times, and so forth. They're not all equal, as you would expect. If you just rolled a dice, you wouldn't get everything to show up equally. Usually you'd see one number jumping ahead. But let's talk about the theoretical probability. The theoretical probability of rolling a 5. Well, you've got 6 different numbers that could show up. So in theory, there are 6 possibilities. Only one of those is a 5. So it's a 1 out of 6 theoretical probability that you would roll a 5. But now we're going to deal with this experiment right here. This is where actually Heather, this young lady, was rolling a 5 and it showed up, you could see 4 times out of 40 trials. So she rolled that cube, that dice, 40 times. 4 of those times, it was the number 5. So we're looking right here. We can reduce that. We can divide by 4, and we'd get 1/10. So these numbers are not the same, and I think that can scare people. They can say, oh no, what's going on? Well, guys, the experimental probability very likely will not equal the theoretical probability. However, if we kept rolling, 40 really isn't all that much. You're going to see this right here. As the number of rolls increases, we would expect the experimental and theoretical to become closer to each other, though they might not be equal. So if we rolled 1,000 times, we would picture that these 2 fractions would actually, and this is going to be your general answer, guys. As you increase the number of trials, as you increase doing this a whole bunch for large numbers, that's when you would get to see the experimental become closer to the theoretical. So that's really all we've got for today. Another way to just look at it, imagine that you're flipping a coin. And if you say, what's the probability of getting heads? Well, the probability of getting heads, you'd say, well, there are two possible things you could get. You get a head or a tail. And, the probability of getting heads, you'd get 1/2. Let's just say that you went ahead and you actually flipped a coin. And you only did it 4 times. The experimental would be out of 4 times, I got a head 3. So the experimental probability might seem to be way, way far off. But if we really started flipping coins a lot, like 1,000 times or even more than that, we would expect the probability of the heads to get closer to 1/2. So that's all we've got for today.